Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Good morning, friends. So today is another physics class. Now I am continuing with the late part of physics. This is the part that you'll see towards the end of the first year or towards the beginning of the second year, based on how physics is taught. For instance, you know, when you when we do waves, we then look at sometimes we do sound and then go on to heat. But some ways of teaching physics involve looking at sound and then light. You know, and so that is often a critical practice. So I am going to take that route. Last year we didn't do that. We went from we first completed electromagnetics, and then in electromagnetic waves, and then we went to light. So this year it is a little bit switched around to give you both models. So in your NCERT textbooks, they don't do light in the first year. They do light in the beginning of the second year. I know that. Now, so this will help students who are in class 12 also, because light will come in the beginning of your second year. But Professor H.C. Verma, in his book, he chooses to do light towards the end of geometrical optics and light waves. He does that towards the end of his presentation of the first year in physics. So in keeping with both these ideas, so I thought I will start there. This year I will little bit switch it around, compared to last year when when we went to light. In fact, after we taught Maxwell's equations. But before that, I'm first going to present, get through, the business of, presenting, of presenting some of our products. So at JnanaMarga, we have a lot of products, and we deal with both the Indian model and the American model, but we are the most affordable model that you can get. JnanaMarga has received a US patent because of the slightly different way we take to education. We are what we would like to think of as a guru and grant company, and which means that we place significant emphasis on students learning to read books, and the format that of books that we deal with is the ebook. We received an award this year at the World Education Summit for innovative technology solutions for school education institutes. We worked with almost 1 year. All these slides that you see, we worked almost 1 year with teams which are based out of IIT Chennai, and our physics program is targeted to both, as is our chemistry program. We help students with JEE, students with NEET also. And so we have our flagship. We ship a tablet just like Byju's. We also ship a tablet version. The only difference between Byju's and us is that it comes with free lectures, and our tablets are, maybe, a 1 year program is only 25,000 rupees with the tablet. And so because of that, we are far cheaper, and we believe, better also. And it includes the teaching staff as well. We have 3 PhDs in our staff. So our program also comes with books, because we are a guru and grant company, as I explained. We give the student H.C. Verma as an ebook in the tablet if you buy the the 25,000 rupee solution, and if you and we also ship the biology and chemistry if you are a Sushruta for NEET student. Then of course you get the NCERT books, because You have to really learn, for both NCRT chemistry and NCRT biology. You have to be completely on top of all the material in the NCRT textbook and more. So I love aspiring doctors, and I want to have many of them become our students. So please join and please take advantage of us. If you've signed up with Baidu, signed up with Vedantu, we are not opposed to anybody. We work with students who are Baidu students, who are Vedanta students, who buy our platform to become, to develop mastery over the NCRT books, and the NCRT curriculum, which is so central if you want to become a doctor. Botany and zoology are 50% of the NEET exam, and you have to be inside the ebook and 100% inside the ebook till you know it so well that nobody can challenge you on the biology textbook. Same with chemistry also. Knowing NCRT in and out is a first passport to pretty much everything in not just NEET exam. For any, you will get very high marks in your boards, etc. Now, this is how it looks. Now, when you open the book, open the app, you will find the syllabus in each of the subjects. Then from the syllabus, you will get the NCRT book. But also, we have references into the ebook, which is available on Kindle for Exiverma if you buy the tablet version. Otherwise, we have a lower end version for students. This is 11,000 rupees. If you sign on, so that version is also a very good version for students to get. We love to have students on board who use that. Today, what is missing in this is a slightly old slide. We have the textbooks. You will get our slides, the slides that I am presenting today. Then you will get the links into the IIT PAL lectures. IIT PAL lectures will do you a world of good, notably for physics and chemistry. You're a Sushruta student. Then what we have added, which is not there in this presentation, is we have added the link to assessment. We now have very good assessment. You can use the assessment as well. Okay? So please go ahead and make your notes also. You can do have note taking, etc. Take your own notes from textbook or slides, and then you will be in great shape. The second platform that we have is Ramanujan for JEE, our second flagship. It is a wonderful platform. Again, for the 25,000 rupees, it will be very well invested. Even if you're studying in Kota, or you're part of Byju's, or you're an Akash student and you're paying them, this is only like 25,000 to buy the tablet. Once you buy the tablet, you will be in great shape. Our tablet also comes with Exiverma, and we also ship you C-Engage Maths with Tibani and Solomon's, and then you will also get the previous year questions. We also have now our Jnana test prep apps, which cover both Sushruta for NEET and JEE, Ramanujan for JEE, and these test prep apps will get you fully going. You'll be able to take quiz after quiz after quiz. And we have they've already been launched, and students used it in the most recent both JEE and NEET exam. So, and all our books are linked with IIT PAL. You can also go to eAbhyas for and you can also take advantage of the Diksha app. So, but most importantly, take advantage of our world-class teachers. So very good set of all-round offering that we offer. Jnana Test Prep is today, increasingly ready to help students gain platforms. The other thing is a lot of our content was developed with help from teams which are based in IIT Chennai. You will also meet our one of our teachers who is actually recent IIT entrant and is a brilliant teacher. You should look at Tarun's lectures for mathematics. Wonderful lectures. Please attend Tarun's lectures. They are wonderful. And so we are also working with Amrita University, and they have given us 4 seats So if you become a student with us, and you take the Amrita exam, that's why you should be studying these platforms. Okay, with that, I'm going to stop explaining our JnanaMarga platforms and then move on to today's business. Because we need to do justice to our work with waves first. So today, as I said, this time we are taking a different approach compared to last time. Last time we began with waves, as we went to light after we went to electromagnetic waves in class 12. This time we have switched it around. We are going to do light early. And so in order to get people introduced to concepts in light, I was first going to quickly revise our material with respect to sound. We first discussed waves, and then the direct a step forward from waves is firstly sound, right? So now, um, so you may remember how we first explained simple harmonic motion, and then we explained how resonance conditions occur, and then we discussed periodic motion, and then went on to waves, right? Now, after we went on to waves, we then discussed the two types of waves. One is uh, transverse waves, and the other is longitudinal waves, right? And then we discussed sound as a longitudinal wave, right? That is where the particles move in the direction in which the sound propagates, right? So the particles move this way and the sound moves this way. But in the case of the transverse waves, the wave moves this way, or the wave energy moves this way, and but the particles, they move in a perpendicular direction, right? So that is a very different model, you know. Uh, so that model is different from this model, you know. So wave different when waves travel, in transverse mode, and the wave moves perpendicular to the direction of the of the energy, right? So that is transverse waves. So mathematical description of a wave is very often there are two aspects to it. There is it's like, you can think of it like, eventually when you study waves, you will also look at this idea of stochastics. In stochastics, you will also look at the idea of what is called a random process. Now, although it is analogous, and I mention it, waves on the other hand, right? They are a function of x and t. So the what does that mean, function of x and t? So for a given t, it is only essentially a function of x. So at any one point in time, you have the wave defined over a particular region, okay, over a particular value of x, right? So the wave is defined over this value of x, and then it's like, some kind of a waveform. So for instance, look at this: a square minus x square and 0, right? So that is a inverted parabola. So in this area, it's like this, right? So now, similarly, right, it is also a function of time. A wave is a function of time, which means that inverted parabola is moving. Okay, so you have the parabola, and the parabola is moving. As time goes on, the function changes, right? And what changes in the function? Essentially, this vt, x minus vt. As time goes on, you get a different parabola, and then another parabola. Okay, so as time moves on, so that is in a sense a wave. So you must understand that aspect of it, at a very basic level, and then when you learn, random processes, it will be, you will see the analog that I mentioned. Okay. Now, a disturbance which is created at f of x at time t equal to 0 will be changing, will be given as a function of time. Okay, and so as many of you know, f of x plus vt, f of x minus vt, right? F of x minus vt is a wave traveling in the x positive x direction. You all know, transformation of functions from mathematics, right? So f of x minus vt it transforms the function in this way, right? F of x plus c naught will push the function up. F of x minus vt will push the function this way. F of x plus vt will push the function this way, right? So a wave moving this way will be of f of x plus vt, and right. So, but if you have f of x together and then you added a constant, that just pushes the function up, right? So that's the, remember these ideas, they come from basic functional mathematics, right? So you take that functional mathematics, you add the idea of wave. Now once you add the idea of wave, there is another way of looking at it. Typically, we say that certain waves, they travel undistorted, dispersionless. The most common wave that travels dispersionless is, of course, the light wave. We all know light from the sun reaches us, several seconds later. If I remember right, 7 seconds. I'm not sure. Don't hold me to it. So it leaves the sun at a time x and travels at 3 into 10 to the power of 8, I think. I'm not sure. I don't remember. Meters per second, right? So it travels at great speed and then arrives on Earth, right? And along the way, right? Because in free space, right, the disturbance travels undistorted. Today, because we are moving from sound to light and we are getting involved with the idea of waves, right? So now and the dispersion travels with a constant speed v, right? And as all of you know, light travels with that fixed speed c, right? Now, many students will eventually learn a little bit of special relativity. Special relativity changes things a little bit, but not that much. When it comes to waves, the speed of light is fixed and constant. There are many forms of light with different wavelengths, right? So, and then we also discuss the idea of wavelength, right? So, but the general equation, this is the general wave equation. Dou square f by dou x square equals 1 by v square dou square f by dou t square. Okay. So now, why is this equation true? Right? This equation is true because of this. And it's written this way. So when you take the derivative with respect to t, and when you take the derivative with respect to x, right, they are related by this: t equals x over v, right? Or t minus x over v and t plus x over v, right? So when you take these derivatives, partial derivatives, you therefore end up with this equation. Okay, so and this is the one-dimensional differential wave equation. Dou square f by dou x square was 1 by v square dou square f by dou t square, right? And what is the why is this equation important? Because every wave follows it. Pretty much all these undistorted waves, they follow it, right? Now, there are of course certain waves that diminish, right? For instance, the sound wave, right? Sometimes, if people speak too softly, the other person cannot hear, because sound moves through a medium, which is a gas, right? Sound cannot move without, in vacuum, right? Sound moves through air, and then it moves through the vibration, and that vibration softens, right? So, and that's how sound, right? So that aspect of sound being heard, right? That's why we have all these amplifiers for sound, right? Which then record the signal using a sensor, and then there's a vibrating sensor which then transforms it into an electrical signal, which is then sent to the other side, hopefully undistorted, right? So the see, in India we place great value to what we call Shabda Brahman, right? The the hearing of this of the sound, right? So so that is a very critical thing that students should also learn. That we as we are intricately linked to these two forms of waves. That is the idea of sound and the idea of light. So these are the most common waves that we deal with. Of course, we have also the wave in the we look at it also from musical instruments and others. There's also sonar waves, which are a kind of sound wave, slightly different frequency. So then we discussed in great detail the relationship between period and the relationship between a period and wavelength, right? Lambda equals mu t, right? Or V equals F lambda, right? And lambda equals Vt and V equals F lambda, right? V equals F lambda, you must definitely remember, the velocity of the wave equals the frequency times the wavelength. Always, that's the most important formula you'll keep in mind. Then we brought in this idea of the wave number. The wave number is related to the to the free wavelength, right? Wave number is related to the wavelength. It is angularly related to the wavelength 2 pi by lambda, while the angular frequency is related to omega. Now k and omega will, between the two, like V equals F lambda, they give you the V equals F lambda. Okay, so one side comes from the angular frequency, the other side comes from the wave number, right? They are it is another way of writing V omega equals Vk is another way of saying V equals F lambda, right? So if you forget omega equals Vk, you can derive it from V equals F lambda, because V equals F lambda, V stays the same, F becomes omega by 2 pi, right? Lambda equals 2 pi by k, right? And therefore the 2 pi's cancel and you end up with omega equals Vk, right? And this is with the phase shift, they add the phi also, so that if the wave is shifted by a phase, so phase shift, right? So transverse waves, longitudinal waves, we discussed. Sound is a longitudinal wave, right? So the particles move like this, the wave travels like this, parallel, right? Now, if you move the rope, that is a transverse wave. The particles in the rope, they move up and down, but the wave moves forward this way, right? So that is a transverse wave. So we discussed all this. We discussed the sound, the speed of sound, etc. Right? So why did I go through great detail of revising this, so that you get some revision, right? But also so that you do some problems, but also because we want to introduce today the beginnings of light as a wave. You know, uh, Now we will revert back to light optics, standard optics, after we do light as a wave. As I said, we are now switching around the way we are doing things. Rather than do it after we do electromagnetic waves to go to light, we are introducing light as a wave after we do sound as a wave. So that is the aim here. And so this is the displacement of the reflected wave equals the negative displacement of the incoming wave. So that is when a wave hits and rebounds. Where in the case of sound, right, the wave hits and rebounds. You would also have heard, all that. If you have, I assume all of you have been watching Bollywood movies. If you have never seen a Bollywood movie, I highly recommend it. Now, Bollywood movies always, like, the hero is singing in a mountain and then he hears the echo, right? And I don't know, let me sing a quick song. Like, there is the song Kora Ka Gasuta, right? And then the mountains reflect his words, right? And therefore that is what is happening here. There is a reflected wave, right? And so that, because there is a difference in the time, right? There is a speed of sound, right? Sound hits and then rebounds, right? So it is not instantaneous. That's why the hero hears himself singing, right? Now, in the case of light, right? Also there is reflection, right? Light, why I'm discussing sound first and then light is, what happens to light is that light is reflected. If you look at a mirror, light is reflected, right? Now, in addition, what else happens to light? Light, when you look through a glass, particularly at an angle, right? There are two things that happen. Even there, light could be reflected. Okay. Then at the same time, light is also refracted. That is, it hits the glass, then it deviates. Like, seam bowling. I don't know how many of you like to watch cricket. Cricket, a seam bowler, when the ball hits the ground, it then deviates after pitching, right? So that is seam bowling, right? So that deviation after pitching is, produced by using clever use of the seam. Okay, and so uh, similarly, when light hits a glass surface at a particular angle, there is an incident angle and there is a refracted angle. But in addition, there are other things that happen to light, and the most common thing that happens to light from the sun is that it gets dispersed. Okay, so now I am going to briefly return, having reintroduced sound, reintroduced waves. I'm now going to go back to the various things with respect to light. So now, so this is a little bit different, as I said, different way of dealing with it. Previous year we did electromagnetic waves, Maxwell's equation, then we went to light, right? This time we're not doing that. This is dealing with the material so that you understand light. Okay, you understand light from first a class 11 perspective, then you will understand it again from a class 12 perspective. Now, what is dispersion? Okay, as all of you know, you've all seen the rainbow, right? What does it tell you? We discussed the wave number and the wave equation, right? And then I quickly glanced through with the superposition of waves, right? Now, light is, has been the treatment of light and the electron itself, right, was later, in later times, there's what is called dual wave, particle wave theory. There they said light is both a wave and a particle. Okay? Same with electron, right? The electron is both a wave and a particle. And that's a very tricky thing. Mostly we deal with electrons as particles, but then it helps also to understand that they are both. In fact, both. This is called de Broglie wave theory. Now, when we look at light, right? Light is also called, just like you have electron, it is made up of photons, and what we call quanta. Now, when we look at light, right? Typically, there is monochromatic light. Okay. Now, a sodium lamp, a sodium lamp produces light of a particular frequency. So that you will understand in great detail when you study chemistry with Tiwari. Now, why? So that when a sodium lamp emits light, it is largely monochromatic. So it is of a single frequency. So there is monochromatic light, and then there is the light of the sun. Sun has many different elements which emit light. Okay, the sun contains carbon, it contains a lot of helium, hydrogen, etc. And and it's the constituent light from the sun that we see as from with our naked eyes, you know, are largely in a certain window. There is there are frequencies that we can physically see with our eyes, and there are frequencies emitted by the sun which are not visible. Okay. Now there are certain frequencies which pass through the atmosphere and show up in on Earth, and there are certain frequencies which do not pass through the atmosphere, and they are blocked out by the ozone layer. Okay. Now the breaking of light into its constituent wavelengths is called dispersion. Now when we look at dispersion, right, we look at this particular idea, the spreading of white light into its component colors. So what are these component colors? Well, first let us list them. VIBGYOR, VIBGYOR, right? VIBGYOR has a different V has a different wavelength, 400 nanometer wavelength, while R has a bigger wavelength, 650 nanometer. Okay, so now the diffraction of light, when white light passes through a prism, right? Remember, I discussed refraction, and I said that that's different. Always remember that. Now certain kinds of material, they end up breaking light into their constituents, and one of them is the prism. Is a prism typically made out of fused quartz, flint glass, etc. Right? Now, of course, all of you have all seen the rainbows, right? They also break up light. Light is the same thing, whether it's broken up by a prism or by droplets of water vapor and water up in the sky, right? Water when it's up in the sky and it disperses, right? Or now the one of the famous scientists called Sir C.V. Raman, right? He's Indian, and both he received the Nobel Prize, as did his nephew Subramaniam Chandrasekhar. Subramaniam Chandrasekhar received it in the more recent time frame. Sir C.V. Raman is most known for his work with dispersion. Dispersion is what causes the changing color that you see in the sky. There are two kinds of what is called scattering that occurs. There is Rayleigh scattering, and then there is Raman scattering. Raman scattering also is an important idea. Where do these ideas matter the most? Dispersion and scattering matters the most. In today, it is a huge part of fiber optics. In optics, the biggest breakthrough in in communications is fiber optics. Notably, it was fiber optics was discovered in 1960s. It is what allows large amounts of data to pass from one place to another. Okay, so I'm giving you more of an introductory idea in today's class, but we will go into the details in terms of the material that you will learn in when it comes to light. So this time we are taking a different approach, a more practical approach. Now, the refractive index is a little bit different for different, like flint glass, crown glass, etc. They have a different refractive index, and it changes with respect to the wavelength. And so this change in the refractive index with the wavelength, right? So what happens here? The refractive index for red pushes the light up there, right? The refractive index for blue pushes the light down here. So light when it hits, if you add just monochromatic light, when it hits the glass, right, it will, like seam bowling, right, refract, right? Now, if you had a ball, cricket ball, which broke when it pitched, right? And Zahir Khan was still bowling. It seemed differently from different post after pitching, or Ishan Sharma. Let us say it pitched and then it uh, deviated. Now different balls deviate differently, right? Now, and the bowler has power to do that. Not so in this case. The red refracts less, the blue refracts more. That is only dispersion. Refraction and dispersion are different from that point of view. This is a very nice picture which explains how each of these two occur, okay, and why there is this idea of light separating into its various colors. It is because of the difference in the refractive index with wavelength. Okay, therefore this deviates more, like the cricket ball breaking up and going 5 ways, and you will definitely get out. One ball will hit the sun. Right? So that's how it works, right? So now there is this thing called Cauchy's relation, which relates the refractive index to the wavelength, and so he had this relation A plus B by lambda square, in order to explain roughly this kind of change in the refractive index with wavelength, and so he said it's related to the wavelength. Okay, so that's why you see this dispersion. Okay, now dispersion can be compensated if you introduce another prism, okay, which then goes the other way. Okay, so you will never see that happen. If your cricket ball breaks, it will never come back together, right? Gone na gaya. You have to buy a new cricket ball, right? So now it is refracted, then it goes to another prism, and then it reintegrates. Okay, so that is potentially possible. Is possible to compensate for the dispersion of the first prism using a second prism. Okay, so now the formation of the rainbow. How did the rainbow form? It forms again because of this variance in the dispersion, but there is a second effect which is called total internal reflection. So we will do total internal reflection and refraction in the next class. Okay, we will go over refraction, sin I by sin R, right? I'm sure you know that from class 9 or 10. You would have heard of this sin I by sin R, is the refractive index. You would have heard of all that, right? So now, but then, first I want to give you the big picture this time, So you have the white light which comes in, refracted differently, and then it then experiences total internal reflection inside the water droplet, and it comes back this way. So it goes, see it like that, then comes back this way, and then you see the rainbow on that side. So there's a droplet falling here. The light comes, it hits the droplet at an angle, right? And then it goes inside the droplet. It comes, hits, refracted here. Sin I by sin R happens here. Snell's law, right? Then it goes inside the droplet. It then is reflected, and then it comes out. Okay, so that is how this partly works. So now the geometry of the prism, you can look at the angle deviation, sin I by sin R. I'm sure you have heard, right? So but learn the geometry little bit, right? Let's look at the geometry a little bit, minimum deviation, etc. Right? So in the case of the prism, because they like to ask tough questions. What can I say, right? So not that tough. This material is not that tough, but we are always trying to be up to it, right? So here is the incident angle I, the refracted angle R, and this is the normal. Let me call this ZPQ is ZPO is 90 degrees. That is the normal, right? So now the incident angle I, and this is the refracted angle R. Okay, so sine I by sine R will give you N, refractive index. Snell's law, sine I by sine R, right? Now, how is, like, then why does it bring in all these angles, right? Angle A plus OPQ plus OQP, that's just the angles of a triangle. 1, 2, 3, right? Equals 180 degrees. So A equals 180 minus 90 minus R minus 90 minus R. Okay, so that's what A equals 180 minus 90 minus R minus 90 minus R. So what is 90 minus R? OPQ. OP, this is 90 degrees, right? So 90 minus R will give you this angle. Okay, so OPQ plus OQP plus POQ equals 180 degrees, right? So, and because of that simple relation, these two angles are isosceles triangle. In the case of minimum deviation, it is not always isosceles triangle. If this angle was not a particular angle, then you won't get minimum deviation. Okay, so this is only when it is incident, so that the PQ is parallel to the base of the prism. That's when you get minimum deviation. Okay, so when that is the case, R equals A by 2. When R equals A by 2, your sine I by sine R, and therefore I, what is I then? I is A plus dm by 2. Dm is what? Minimum deviation angle. So sine of A plus dm by 2 divided by sine of A by 2 will give you the what is that? This one. N21. N21 is what? The refractive index going from air to the material of the prism. Okay, so now this is just a sine inverse formula he's taking, right? Sine inverse formula. If you write, if you cross multiply and write the sine inverse of what remains, you will end up with this formula. You see, this is just, he's just cross multiplying and then taking the sine inverse of both sides. Therefore, he ends up with 2 sine inverse this one, and then he takes the A to the other side in order to calculate a dm. Okay, so he is explaining, if you needed to calculate the minimum deviation, this is how you do it. PQ is not always parallel to this. It is parallel, only when it is parallel do you get minimum deviation. All right, so that is this minimum deviation angle. How to calculate it? So for a thin prism, sine theta, thin prism, A is very small, sine theta equals theta for very small angles, right? Therefore, the the minimum angle also becomes small. Sine theta equals theta. Substitute it into sine of A plus dm by 2 divided by sine of A by 2. If this whole thing is sine theta by theta, so theta 2 by theta 1, then you can have dm equals A times n minus 1. You end up with a formula. You should, if you spend little time doing the maths yourself, let's say the teacher, you spend little time doing the maths, you will remember and you will be able to do it when you need to do it. Okay, so dispersion of prisms, the material is calculated for a specific wavelength, was sine of A plus dm by 2 divided by sine of A plus A by 2. For thin lenses, you have A times n lambda minus 1, right? And therefore, you end up with dB minus dd. What is dB minus dd? What is d? D is the deviation angle. And what he is saying is that the angles are very small. So for mirrors, there is no dispersion. Light just hits the mirror and comes right back at you, right? So it's like, we discussed echo, right? Pura Kagasda, right? Remember, maybe you are all too young to know old Hindi songs, but I thought I will provide you a perspective there. So this is the introduction to dispersion. I did want you to understand dispersion and vocalize all the parts to it, and give you the a feeling for the material. Otherwise, if you just understand, physics in without understanding, just the math side of physics, you can understand that also. It's good to understand only the math side. Then you can always, the perspectives of these things will also come eventually. But it's good to also, read a textbook like H.C. Verma, but also, learn these things in great detail. Like for instance, many teachers, they try to teach physics little bit with the story that goes with it, right? Physics is a beautiful story, right? Now, so and so in discussing that story, we always show Newton, right? Newton is intimately, in our pictures, when we particularly do a lot of mechanics, we always show a lot of Newton, right? Now, Newton is also intimately related to this prism. He also did a lot of work in light, and in those days it was, it was always magical. People looked at light and it was pure magic. Even today, if you ask me, light is magic. So wave optics, right? So now we introduce this idea of what is called Young's double slit experiment. Having understood light as being a wave, having understood light as containing many frequencies, that is, natural light as containing many frequencies, and stating that there can be light which is of only one frequency, right? We will then introduce this idea of Young's double slit. Okay, so Young's double slit experiment uses two coherent sources of light. What does that mean? Coherent sources of light placed at a small distance apart, usually only a few orders of magnitude greater than the wavelength light is used. All right. So one must understand every detail in some of these things to appreciate the science that went into it. Okay. So the preciseness of the science that we use, the knowledge that was gained by people like Young, doing an experiment many years ago, right? Now, in the modern world, lasers, what is laser? Light amplification by stimulated emission of radiation. So lasers, they produce what is called coherent light. That is, it's not light which is, differently wavelength and differently, oriented. All the light, the phases are not different. They all come with the same phase. They're all like, like if they were all in a symphony, all the light that came from a laser, they will make great music. Okay? So what they mean is that they are coherent. That's what they mean by coherent. So I wanted to relate that idea to you, so that now the light comes and there is a like a opaque medium with two holes. So let me show you, Young's double slit experiment. So there is coherent light coming this way, right? Then it hits a two slits. That's why it's called double slit experiment. So this is this whole thing. This is an opaque surface. There's light coming in. It hits these two holes, small slits, right? And then it it on the other side, you see, you understand the wave nature of light, then goes as waves on the other side. Okay, and so now what you see on the other side, right? Normally light is just bright, right? On the other side, what they found when they had coherent light applied with the slits is they found lines. Okay, and what uh, caused and separated these lines? What caused and separated these lines was that these waves, in some places, where it would produce a dark line, and then it would produce a bright line, dark line, bright line. Okay, why did that happen? Because in certain places, the two waves would cancel each other and therefore produce a dark line. And then just a little bit below, it would produce a white. Okay, so that was Young's double slit experiment. So why did it produce these dark lines and white lines? Now uh, it is because this because of the wave nature of light. And that the waves, if you had sine omega t and minus sine omega t plus pi a sine omega t plus a sine omega t plus phi, right? So you have the sine wave like this, and then you have the sine wave shifted like that, right? So one is going up, the other is going down. So they differed by a few wavelengths. Okay, therefore, as a result, they were either additive or they were subtracted in that at that particular location. Okay, so that formed the basis of Young's double slit experiment, and that went on to provide the wave understanding of monochromatic coherent light emitted by a laser. So this is Young's double slit experiment, monochromatic light sources, separated by wavelengths. So how do you look at the two waves, right? So the slit S1 had this wave, the slit S2 had this wave, right? And these two waves, when they reached here, they were completely out of phase. Okay, so that's why I introduced you reintroduced at the beginning of the class the wave theory, because I wanted to redo it this time, not after electromagnetic waves, but in the context of waves, and therefore I reintroduced it. So now when they are out of phase, they then cancel each other. So this difference in distance between S1P and S2P, roughly speaking, what is this length? And this length had to be, a sub wavelength. Okay? So these distances were all related. Okay, so now light, as we already saw with dispersion, right? Minimum angle, right? Is always you have to understand the wave nature of light and the geometry of it. Optics is about geometry. Okay, so you must know, how to distinguish. You must then look at the geometry associated with these distances, and the difference in the distance is a sub-wavelength. It has to be exactly that in order to produce the dark spot. And if it produces a bright spot, it has to be exactly in sync. Okay, so if it produces a bright spot at point P, then this distance has to be perfectly end wavelengths. Okay, therefore that's why you find dark and bright, dark and bright. They were exactly pi different, a difference of pi, then upper sign, lower sign cancel out. Okay, so that's the mechanism. Okay, and this phenomenon uh, is is related to this idea of diffraction. Okay, so where is the diffraction? Diffraction, when a wave encounters a obstacle or an opening, it is defined as the bending of waves around the corners or through an aperture. That is diffraction. Diffracting object of aperture effectively becomes a second source of the propagating wave. Okay, so diffraction slightly different, okay, but actually hugely different. Okay, refraction, diffraction, dispersion, three different ideas, and all these come into play when you look at light. Okay, so with that, I'm going to close today. We've kind of reached the end of the hour. Um, but what I will suggest is for a lot of students to read the material that we went over and get started with optics. We will try to do optics in 2 or 3 classes, and then we will move to heat. But because as I said, I'm three. No, actually, optics may take 3, maybe even 4 classes. I'll complete it in good time. But then we will go to heat again. And then we will work on heat. Okay. So so this is the phase, dealing with these ideas. If light comes off into the first year, heat typically will move to the second year. But then we will try to add have that bridge. So in fact, this class is very useful for the students, NCRT material, the CBSE students. It starts at the beginning of the second year, that is class 12. But then, H.C. Verma, in all his wisdom, Professor H.C. Verma has added it to the first year material. So this time I'm teaching it, along with the class 11 students. All right. So with that, I'm going to end today's lecture, and I will see you all next class, and we will continue the material on light. Okay. So okay. So I will. Thanks for joining us for another presentation of physics.